In this lecture, we're going to talk about complex numbers. So complex numbers arise very naturally when finding solutions to equations. So for example, if you wanted to find the x values that solve this equation right here, x squared plus 1 is equal to 0, well, the methods that we have so far to actually try to solve this are to either factor this, or maybe you could isolate the x squared and take square roots of both sides. So looking at this, you could try to attempt a factorization, but you will not be able to find one where you actually have real numbers, okay? So let's try to solve this by isolating the x squared. So how would you do that? You bring the negative 1 over here, so x squared, subtract 1 from both sides. And then now what would we do? Well, at this point, we could take the square root of both sides, okay? So I take the square root of x squared, and that'll be equal to the square root of negative 1. And what is the square root of this? Well, that's the absolute value of x, right? So that means that x is equal to square root of negative 1 or the negative of that. Whoops. Or x is equal to minus square root of negative 1. Okay, but here's the interesting thing, right? You want to take the square root of a negative number. Well, that's going to present an issue to you if you're trying to find a real number that finds that, right? Because if you were to find one, then I should be able to square it and get negative 1. However, you're not going to be able to find a real number that you can square and get a negative, because we know that if you square anything, it should be non-negative, right? So this is not a real number. Not in the sense that it doesn't exist, it's just it is not on the real line, okay? You can't find that number on the real line. It's not on the real line, okay? So what we have to do historically, what was done was we just extended our notion of numbers, okay? And we call this a new number, okay? So we call that the imaginary unit. Okay, imaginary unit, and we call that I, okay? So we just denote that value as I. And that's not going to be a real number. You're not going to find it over here on the real line. But that is an example of what's called a complex number. Now, I don't particularly like the naming of it because it makes it seem like it is not real, like doesn't exist, but it is imaginary in the sense that it is not a real number. So I guess it is sort of a nice naming, but still it makes it seem like this is illegitimate, okay? So just from this point on, you don't have to remember like where it came from, but at least you see the context of why we have to introduce such a thing, okay? Because this would be the solution, and we're just going to denote that as I. So from now on, just remember that I is going to be the square root of negative 1. In other words, what would that mean? I squared is equal to negative 1. That's another way to remember a property that, the definition of I. So this is actually the definition, okay? And another thing that we're going to use as we simplify some of these roots over here, because they have negatives, okay, that's the new part, is the following. Let's say that I want to take the square root of negative a. Well, we have properties of roots that say that we could break that up, right? Negative a is the same thing as negative 1 times a, right? And we could break that up as the square root of negative 1, square root of a, and this negative 1 the square root of negative 1, we just gave that a name. We gave that I. So we could just write it like this. So that is square root of negative a you could just write that as I square root of a. All right, and that's another sort of useful thing to remember. If you forget it, of course, you could sort of redo this derivation here. Okay, so you're just going to pick up that I when you take square roots of negatives. So let's try to simplify some of these roots. So what happens if you try to take the root of negative 49? Well, you could either remember that you can immediately jump from negative 49, the root of negative 49 would be I square root of 49, okay? Or you could break this up in the exact same way that we're doing here. So this is going to be I root 49. So you're essentially bringing the negative out as the square root of negative 1, which is I. And what is the square root of 49? Well, that's 7, right? Because 7 squared is 49. It's customary to write the I after the real number like this. So even though that I times 7 is correct, it's just customary to write the real number in front of the imaginary unit. Well, what about this one here? Negative square root of negative 81. So this would be negative, and then that negative here would come out as the square root of negative 1, I, 81. Okay, so this negative is right here. This square root of negative becomes the I, and then what's left over is the square root of 81, and we know that that is 9 because 9 squared is 81. So we would write this as negative 9I. What about square root of negative 48? Well, we would write that as I square root of 48. And the examples up above, we always had a perfect square, but do we have that in this situation? Well, no, we have 48, but could we factor 48 so we have a part of it that is a perfect square? Well, we could write this as 16 times 3, right? And the square root of 16 is 4, so we have I times 4 times root 3, and we would probably write this as 4I, right? We'll put the real number in front of the imaginary, and then root 3. Continuing on, we have the negative of root negative 75, so this would be negative I, right? This part, the negative is just carried along, but then the square root of the negative becomes the I, and then square root of 75. And can you think of the perfect square that's a factor of 75? Well, that would be 25, right? 25 times 3. And so this is square root of 25, square root of 3, and square root of 25 is 5. So we have negative I times 5 times root 3, and we could write this as negative 5I root 3. Okay. Now we're asked to do the following. Write each of the following as either I, negative 1, negative I, or 1. So why are we doing that? Well, it turns out when you take powers of I that you can always simplify it into one of these 4. Why is that? Well, recall that I is defined as the square root of negative 1. So what that means is that I squared is negative 1, right? So what is I cubed then? Well, I cubed is I squared times I, but I squared we figured out is negative 1. So that means this is negative 1 times I, so that's negative I, right? Well, maybe I should write that as an intermediate step. So that's negative 1 I, so this is negative I. So I cubed becomes negative I. I squared is negative 1. What about I to the 4th? Well, I to the 4th is I cubed times I. And we just figured out I cubed is negative I. And then this would be negative I squared. And what's I squared? I squared is negative 1. So this is negative 1. So that's actually positive 1. So I to the 4th is positive 1. Okay. And then if you do I to the 5th, this is I to the 4th times I, and I to the 4th is 1. So then we get 1 times I, which is just I. But then if you come all the way back to the first power, just I to the 1, that is I. So you see what's actually happening here is you sort of have this cyclic behavior. I to the first is I squared is -1, I cubed is I to the fourth is 1, I to the fifth is I, and that pattern continues on. So what we get is sort of this following pattern. So this work tells us this. So let me just kind of write this out. I squared was -1, I cubed was I to the fourth is 1, and then now this pattern is just going to continue. So I to the fifth is I, right? And then when you go to get I to the sixth, that'll be I to the fifth times I, but we already figured out what that would be, right? That would be -1. So I to the sixth is -1, right? So you see this pattern continues. So like every, it cycles between these four. I, -1, I, 1, I, -1, I, and so on. So really what you just got to do is you can reduce your problem into just looking at these four situations here, right? So what we can do is, this is sort of the key. If you can pull out a bunch of I to the fourths, all of those are just the number 1. So could we do that with I to the 31? Well, can you think, okay, well, you could rewrite 31 as, 4 plus 4 plus 4 plus 4 plus 4, and then you have some remainder. But what is, what's the nearest multiple of 4 to 31? Well, that would be 28, right? So do we agree that this is 28 plus 3, right? 31 is 28 plus 3. And so what is this? Well, this becomes this. Now, why did I do that? Well, I to the 28, this is 4 times 7, isn't it? So what I just did right here was I figured out the closest multiple of 4 that's to 28, but a little bit less than it, right? And then now I have I to the fourth to the seventh I cubed. And now I know what all these things are. You see, I to the fourth is this 1. So I have 1 to the seventh, and I cubed is -I. So what's 1 to the seventh? That's just 1, and -I is -I. So this is -I. Okay. Let me show you another way to do that one, just so maybe you'll think this way is a little bit easier, actually. You know what? Let me switch to a different color here. So let's switch to a blue. Okay, so that's so here's solution 2. Okay, so I to the 31. I could also use the fact that I squared is -1. All right, maybe this will be easier for you. So I to the 31. Do we agree that that's I to the 30 times I, right? But what's I to the 30? That's I squared to the 15th times I, and I squared is -1. So this would be -1 to the 15th times I, and 15 is an odd. So if you take -1 to a power is either -1 or it's 1, right? -1 squared is 1, but -1 cubed is -1. So -1 to an odd is negative, so I get -I. So maybe that's a little bit easier because the solution method that I'm using in this one is to use the fact that I squared is -1. And then you don't have to use this multiple of 4. You're really just decomposing this as, I to an even, and then that's going to be a little bit easier. So let me show you that with I to the 37. So how could we rewrite this? We could write this as I to the, it's already odd, so I need to write it as I to an even. The closest one that's less than it is 36, right? Just one less than it, and then times I. And then I to the 36 is I squared. What's this divided by 2? Well, that's 18. and then I squared is negative 1. And negative 1 to an even is going to be plus 1. So this will just be plus I. Okay, I think that's probably a little bit easier to follow, because if it's odd, just save one of them, and then what's left over will be an even number of them. You rewrite that as I squared to, half of it, and then this power is either going to be even or odd. So how about this one here, I to the 42? Well, I to the 42 is I squared to what power? Well, 42 divided by 2 is 21. And I squared is negative 1. So this is negative 1 to the 21. And negative 1 to an odd is negative 1. So that's negative 1. So I think that's probably an easier method. Of course, you could use this procedure that it repeats every 4, but I don't know. In the end, this is probably the easier method. Okay, now let's just do some sort of basic algebra with complex numbers. So if I have 4 plus I and I want to add that to 3 plus 2I, how do you combine these? Well, the 4 and the 3 are considered like terms because they don't have any i's in them. So we would just add those, and that would be 7. And then I plus 2I, well, those are like terms, so you would add the coefficients. So 1 plus 2 is 3, so I'd have 3I. Down here, you could write this intermediate step if you want, but I think that was pretty clear. So here, what would we have? Well, you know what? I can move some terms around. So 7 plus 3, those are the like terms, right? These two are like terms, so we'll combine those. And then plus 2I minus 4I, right? Those are the like terms that we'll combine. So 7 plus 3 is 10, and then 2I minus 4I will give us minus 2I. So what I was just saying is you could do this intermediate step. It's not necessary, though. Just identify what's like terms and combine coefficients like we've kind of been doing with polynomials and other terms. We've dealt with many situations like that. So here we have 6 plus 7I minus 4 plus I. So here, I think it's good to actually simplify this first, because this negative is going to get distributed. So we have to be always really careful of that, right? It's a very common error. Subtract I. And so this will be 6 minus 4 is 2. 7I minus I is 6I. All right, now let's do some multiplication. So if we are multiplying, we are going to distribute just like we have been doing with any other situation. So this would be 6I, and then plus 2I, 4I, and we'll figure that out. So 6I is 6I. We'll leave that alone for a second. But 2 times 4 is 8, and then I times I is I squared. And then 6I plus 8, and then what is I squared? Well, that's negative 1. So this is 6I minus 8. And we're not going to be able to combine those anymore because one has an imaginary unit, the other one doesn't. It has I, the other one doesn't. So let's do this one. So 11I times 2 minus I times 11I. So this will be 22I minus 11I squared. So 22I minus 11, and then I squared is negative 1. So this will be 22I plus 11. Okay, how about this situation here? So we have two binomial terms that happen to have imaginary units in them, and we're going to multiply. Well, we'll just do what we've always done when we have binomial terms. We will FOIL. So we will do 2 times 3 is 6. Then we'll do 2I. Then we will do minus 12I. And then we will multiply the last ones, and we will get minus 4I squared. So this is 6 plus 2I minus 12I minus 4, and then this will be a negative 1, the I squared. So this is 6, and I should have combined these in the previous one, but 2i minus 12i will be minus 10i, and then minus 4 minus 1 will be plus 4, and so we will have 10 minus 10i. In the next example, we are squaring this binomial term, so let's rewrite it. 6i minus 5i, 6 minus 5i. And let's FOIL. So 6 times 6, 36. 6 times minus 5i is minus 30i. And then another minus 30i. And then plus, minus minus is plus, 25i squared. So this would be 36 minus 60i, right? Minus 30 is minus 60, plus 25 times negative 1. So this will be 36 minus 60i minus 25. So that means we will have 11, right? 11 minus 60i. Okay, so let's move on to some rational expressions that happen to have imaginary units in them. To simplify these, to simplify rational complex numbers, you'll use this trick. You will multiply by you multiply by 1 using the conjugate. So here's what I mean. So let's say that you have something, you know what, let me just say that you have something, whatever that is, divided by a plus bi. Okay, now how do you simplify this? What you're going to do is you're going to multiply by 1, okay? And kind of similar to what you did with the conjugates with radicals. Okay, the conjugate in this situation, the conjugate of the denominator, you will have if it's complex, you'll have a real number, and you'll have a real number times I, right? And so the conjugate will be a minus bi. It'll just be the negative. You'll put a negative in front of whatever happens to be the imaginary part of it. Okay, so that's the trick that you're going to use, and this can be anything. That's why I kind of just wrote it as a scribble. Okay, that's what you're going to have to do. So the conjugate. So note the conjugate, or how about I write this? These two are conjugates. A plus bi and a minus bi are conjugates. So if you happen to have a minus bi in the denominator to start with, then the conjugate would be this, the a plus bi. Okay, so over here, what do we actually have? Well, we have an a plus bi. What's a over here? A is 0, right? That's just the real part. And then the imaginary, you see, that's the I. That's what we have here. And we're going to put the negative in front of that. So what we're going to do is we're going to multiply by negative I over negative I. Okay? That's the conjugate. These two are conjugates. Okay, now simplify. So we have 3 plus 4i times negative I, and then in the denominator it would be negative I squared. Top, you are going to have to distribute this negative I into these two parts, and so you'd have negative 3i, and then you have negative 4i squared. And then down here, negative I squared, what's I squared? Well, that's negative 1. So then this is negative 3i minus 4 times negative 1, right? The I squared is negative 1. Negative 1 is just 1. So you see, I got rid of that I in the bottom. It just became a 1 by doing this conjugate trick. And so in the end, we have negative 3i and then plus 4. Or you could write it as 4 minus 3i. Okay, that's the answer. Okay, so down here, what's the conjugate of the denominator in this expression? Well, this one's actually a little bit easier to look at because I have the real and the imaginary part kind of separated. So the conjugate is going to be 4 plus 5i. Okay, and let's see what happens when we do this. It works out. It's kind of similar to what happened when we were multiplying by conjugates with radical expressions. You end up not having middle terms, and then the two terms left over kind of simplify really nicely. So what do we have? We have 3 times 4 plus 5i. And then we'll have something that we'll have to FOIL on the bottom. 4 minus 5i, and then 4 plus 5i. So we will have 12 plus, distributing, 15i. And then in the denominator, we have 4 times 4 is 16. And then you see that these are opposite signs, so there's not going to be any middle terms. But let's see that. We'll have 20i, and then minus 20i, and then we'll have minus 25i squared. And so this is 12 plus 15i. These two middle terms are just negative, so they are gone, like we said. And then 16 is still there. But then what is this? This is negative 25, and I squared is negative 1. So this becomes 12 plus 5i over 16 plus 25. Right? So that would be 41 in the bottom. And this is pretty much it, right? You could break this up now and look, you have 12 over 41 plus 5i over 41, or we could put it like this, and that looks good. So the idea for simplifying rational expressions with imaginary units is to not have imaginary units in the denominator anymore. We want to rewrite it so it is a complex number.